Tonight, we're going to talk about light, not in a rush way, not as a list of equations, but as a quiet journey. A journey from a soft beam of morning sunlight on a window to the glow of distant stars, to the strange idea that light can behave like both a wave and a particle. Light is one of the most familiar things in the world. It fills a room. It touches the surface of water. It passes through glass. It paints the sky blue. It turns clouds golden at sunset. It travels from the sun to the earth. It travels from distant stars across the darkness of space. And it allows us to see. Almost everything we know about the visible world comes to us through light. The shape of a tree, the color of a flower, the brightness of the moon, the glow of a city at night, the shimmer of rain on a window, the first pale line of dawn. Light seems simple because we live inside it every day. But the more slowly we look at it, the stranger and more beautiful it becomes. Light is energy. Light is motion. Light is an electromagnetic wave. Light is made of photons. Light can reflect, bend, scatter, interfere, and carry information across the universe. It is both ordinary and mysterious. You do not need to memorize anything tonight. You do not need to solve problems. You do not need to understand every detail all at once. Just listen slowly. Let each idea arrive gently. If one part feels clear, let it be clear. If another part feels strange, let it remain softly strange. Physics often begins this way, with something familiar, a candle flame, a window, a beam of sunlight, and then, little by little, we realize that the familiar thing is connected to the deepest structure of the universe. So take a slow breath, let your body settle, and imagine a quiet room in the early morning. The air is still. The world is not fully awake yet. A thin beam of sunlight enters through a curtain. It cuts gently across the room. Tiny dust particles drift in the beam. They appear and disappear as they pass through the light. The room was already there before the beam arrived. The dust was already floating. The air was already moving softly. But the light reveals it. Light does not only illuminate objects. It makes hidden motion visible. And tonight, we will follow that light. From the window, to the sun, to color, to waves, to photons, to the stars, and to the quiet edge of what we can know. Chapter 1, A Beam of Morning Light. Let us begin with the simple beam of sunlight in a quiet room. You may have seen it many times. A shaft of light entering through a small gap in the curtains. It seems almost solid. A bright path through the air. But light itself does not fill space like a piece of cloth or smoke. What you see in the beam are tiny particles in the air scattering some of the light toward your eyes. Dust, tiny droplets, small bits of material floating gently. If the air were perfectly clear, the beam itself would be much harder to see from the side. You would see where the light lands. On the floor, on a wall, on a table. But the path through empty air might appear almost invisible. This tells us something important. We usually do not see light itself in empty space. We see light when it enters our eyes. We see objects because light interacts with them, reflects from them, or is emitted by them. A lamp glows because it emits light. A page is visible because it reflects light. A glass window is visible partly because it reflects some light, transmits some light, and bends some light. A dust particle in a beam is visible because it scatters light. Seeing is interaction. Light travels. It meets matter. Matter responds. Some of the light reaches your eyes, and your brain creates a visual world. Even a quiet beam in a room is therefore full of events. Light from the sun traveled through space. It entered Earth's atmosphere. It passed through a window. It scattered from dust. It reflected from surfaces. It reached your eyes, and then it became experience. The beam seems peaceful, but it contains a journey of about 150 million kilometers from the sun to Earth. Sunlight takes roughly 8 minutes to reach us. When sunlight touches your window, it has just completed a journey through space, a journey at the fastest speed allowed in the universe. The speed of light in empty space Light travels at about 300,000 kilometers per second. That number is enormous, too large to feel directly, but we can imagine it gently. Light can circle Earth about 7.5 times in 1 second. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest stars takes years. Light from distant galaxies can take millions or billions of years. So the beam in the room is not only a local thing, it is a messenger, a small piece of solar history, arriving quietly on the floor. Chapter 2, Light as Energy. At the simplest level, light is the way energy travels. This is one of the most helpful ways to begin. Light carries energy from one place to another. The sun sends light outward. Some of that light reaches Earth. It warms land and ocean. It powers photosynthesis in plants. It drives weather and climate. It makes vision possible. A candle sends light into a dark room. A lamp sends light onto a page. A star sends light across space. In each case, energy is moving. Light does not need air to travel. This makes it different from sound. Sound is a vibration traveling through materials such as air, water, or solid matter. If there is no material medium, ordinary sound cannot travel. That is why space is silent in the usual sense. But light can travel through empty space. It can cross the vacuum between the sun and Earth. It can travel from distant galaxies to telescopes. It can move through the emptiness between stars. This is because light is an electromagnetic wave. We will explore that idea slowly later. For now, we can hold the simpler thought. Light is energy that can travel even through empty space. When light reaches matter, it can do several things. It can be absorbed. It can be reflected. It can be transmitted. It can be scattered. It can be bent. Absorption means a material takes in the light's energy. A dark surface absorbs much of the visible light that reaches it. That absorbed energy can become heat. This is why dark surfaces often warm more in sunlight than bright reflective surfaces. Reflection means light bounces from a surface. A mirror reflects light in a very organized way. A white wall reflects light in many directions. Transmission means light passes through a material. Clear glass transmits much of the visible light that enters it. Scattering means light is redirected in many directions by particles, molecules, or rough surfaces. The blue sky exists because air molecules scatter shorter wavelengths of sunlight more strongly than longer wavelengths. So light is not passive. It meets matter and produces effects. Warmth, color, reflection, vision, chemistry, life. A single beam of sunlight can warm your hand, brighten a room, cast a shadow, and feed a plant. This is why light is central to both physics and life. It is one of nature's great carriers of energy and information. Chapter 3, Shadows and the Straight Paths of Light. One of the first things we notice about light is that it often travels in straight lines. A lamp casts a shadow. Sunlight through a window forms a bright rectangle on the floor. A flashlight creates a cone of light in dusty air. A tree blocks sunlight and creates shade. A shadow is formed when something blocks light from reaching surface. The object stands between the source of light and the surface behind it. Where the light cannot reach, a darker region appears. This is simple, but it reveals an important property. In a uniform medium, light travels along straight paths. That is why shadows have shapes related to the objects that cast them. A round ball can cast a round shadow. A hand can cast the shape of fingers. Leaves can scatter patches of sunlight across the ground. But shadows are not always perfectly sharp. Their edges can be soft. This happens because light sources often have size. The sun is not a single point in the sky. It has a visible disk. A lamp bulb has an extended glowing surface. Because light comes from different points across the source, some regions behind an object receive partial light. This creates a penumbra. The full dark central region is called the umbra. The softer partial region is called the penumbra. We see this in eclipses. During a solar eclipse, the moon blocks sunlight from reaching part of Earth. In the umbra, the sun is fully covered. In the penumbra, it is only partly covered. A shadow on your wall and an eclipse in the sky are connected by the same geometry of light. Light travels. Objects block it. Dark regions form. Partial regions soften the edge. This is one of the pleasures of physics. A small everyday observation can echo at cosmic scale. A hand shadow on a wall, the moon shadow on Earth, a tree's shade on a summer afternoon. All are part of the same quiet rule. Light moves in paths. Matter interrupts those paths, and shadows appear. Shadows are not things by themselves. They are absences. They are places where light has not arrived. A shadow is a shape made from missing light. That is a soft and beautiful thought. Darkness, in this case, is not an object. It is a trace of light being blocked. Chapter 4, Reflection. When light meets a surface, some of it can bounce away. This is reflection. Reflection is why we can see many objects that do not produce their own light. A book does not glow in the dark by itself. A stone does not shine like a star. A tree does not usually emit visible light. We see them because light from another source reflects from them into our eyes. A mirror is a special kind of surface. It is smooth enough that light reflects in an organized way. The angle at which light arrives equals the angle at which it leaves. This is called the law of reflection. You do not need to hold the formula. Just imagine a ball bouncing from a very smooth wall. It comes in at an angle. It leaves at a matching angle. Light reflects similarly from a smooth surface. This organized reflection allows a mirror to form an image. The light from your face reaches the mirror. The mirror redirects it. The light enters your eyes. Your brain traces the rays backward and interprets an image behind the mirror. That image is not a person behind the glass. It is a carefully organized pattern of reflected light. Most surfaces are not smooth like mirrors at microscopic scales. A wall, paper, cloth, or stone may look smooth to us, but at the scale of light it has many tiny irregularities. Light reflecting from such surfaces is scattered in many directions. This is called diffuse reflection. Diffuse reflection is why you can see a page from many different angles. The page sends light in many directions. A mirror sends light in a more organized pattern. Reflection also gives the world its visual texture. A wet street reflects city lights because water smooths the surface. A calm lake can mirror the sky. A rough lake breaks the reflection into shimmering fragments. A polished metal surface flashes brightly. A matte surface glows softly. Every surface has a relationship with light. Some absorb, some reflect, some scatter, some transmit, and through these interactions, the world becomes visible. Reflection is one of light's quiet conversations with matter. A surface receives light, then sends some of it away. And in that returning light, we see shape, color, brightness, and form. Chapter 5, Refraction, or the bending of light. Light can also bend when it passes from one material into another. This bending is called refraction. You can see refraction in a glass of water. Place a straw in a glass, and the straw may appear bent or broken at the water's surface. The straw has not changed shape. The light from the straw bends as it passes from water into air. Your eyes interpret the bent light as if it had traveled in a straight line, so the straw appears displaced. Refraction happens because light changes speed in different materials. In empty space, light travels at its maximum speed. In air, it travels almost as fast. In water, glass, or other transparent materials, light travels more slowly. When light enters a new material at an angle, one side of the wavefront slows before the other side. This causes the direction of travel to change. The light bends. Again, we do not need to calculate anything tonight. Just hold the image. Light enters water. It slows. Its path changes. Refraction is why lenses work. A lens is shaped to bend light in a controlled way. A magnifying glass bends light so that objects appear larger. Eyeglasses bend light to help focus images properly on the retina. Camera lenses bend light to form sharp images on sensors or film. Telescopes use lenses, mirrors, or both to gather and focus light from distant objects. Microscopes bend light to reveal tiny structures. So refraction gives us tools for seeing. It helps correct vision. It helps explore cells. It helps study stars. A simple bending of light becomes a way to extend human perception. Refraction also creates natural beauty. A prism separates white light into colors. A raindrop can act like a tiny prism. This is part of how rainbows form. Light enters a drop. It bends. It reflects inside. It bends again as it leaves. Different colors bend by different amounts, and the white sunlight spreads into a spectrum. Refraction reminds us that light's path is not always fixed. It depends on the medium: air, water, glass, ice, the atmosphere. Light responds to the material through which it travels, and in that response, the world becomes bent, magnified, focused, distorted, and colored. Chapter 6. The colors inside white light. White light may look simple, but it contains many colors. Sunlight appears white or slightly warm to our eyes, but it is made of a broad mixture of wavelengths. When those wavelengths enter a prism, they separate. Red bends less. Violet bends more. Between them are orange, yellow, green, blue, and indigo. This spread of colors is called a spectrum. A spectrum is light unfolded. It is the hidden structure of white light made visible. Isaac Newton famously studied this by passing sunlight through a prism. He found that white light could be separated into colors and then recombined into white light. This showed that the prism was not creating the colors from nothing. The colors were already present in the white light. The prism was simply separating them. Color is connected to wavelength. In visible light, red has a longer wavelength. Violet has a shorter wavelength. Our eyes contain cells that respond to different ranges of wavelengths. The brain combines those responses into the experience of color. Color is therefore both physical and biological. The wavelength exists in the light. The perception of color happens in the visual system. A red apple is not red in isolation. It absorbs many wavelengths and reflects more of the wavelengths we perceive as red. Under different lighting, the same apple may appear slightly different. A white shirt looks different under sunlight, candlelight, fluorescent light, or a blue evening sky. This is because the light illuminating it has a different mixture of wavelengths. Objects do not simply have fixed colors independent of light. Color is a relationship between the light source, the object surface, the surrounding environment, the eyes, and the brain. This relationship gives the world its richness. The green of leaves, the blue of the sky, the gold of sunset, the silver of moonlight, the violet glow of neon. Every color is a meeting between light and matter, and every color is also an interpretation made by the living eye. Chapter 7. Why the Sky is Blue. One of the most familiar questions about light is this: why is the sky blue? The answer lies in scattering. Sunlight enters Earth's atmosphere as a mixture of colors. The molecules in the air scatter shorter wavelengths of visible light more strongly than longer wavelengths. Blue light has a shorter wavelength than red light, so blue light is scattered more strongly through the atmosphere. When you look away from the sun into the sky, you see this scattered blue light coming from many directions. That is why the sky appears blue. The air is not blue in the way paint is blue. Rather, the atmosphere redirects sunlight in a wavelength-dependent way. It sends more blue light toward your eyes from all over the sky. This process is called Rayleigh scattering. The name is technical, but the idea can be gentle. Tiny air molecules scatter shorter waves more strongly. Blue light gets spread around. The sky glows blue. If Earth had no atmosphere, the sky would look black even during the day. The sun would shine, but the space around it would remain dark. The blue daytime sky is an atmospheric gift. It is sunlight made visible by air. Clouds appear white because their droplets are much larger than air molecules. They scatter many visible wavelengths more evenly. That mixed scattering appears white or gray. So the blue sky and white clouds are both results of scattering, but by different kinds of particles. Air molecules scatter selectively. Cloud droplets scatter broadly. This gives us the familiar contrast. Blue background, white cloud, a quiet painting made by sunlight and atmosphere. The next time you look at the sky, you might imagine sunlight entering the air and being gently redirected by countless tiny molecules. A soft blue glow arriving from every direction. The sky is not a surface. It is a depth of air scattering light. A vast, luminous atmosphere. Chapter 8. Why Sunsets Turn Red. If the sky is blue because blue light is scattered strongly, then why do sunsets turn red and orange? The answer is also scattering. At sunset, sunlight travels through a much longer path in the atmosphere before reaching your eyes. When the sun is high overhead, its light passes through a shorter column of air. But when the sun is near the horizon, the light travels diagonally through much more atmosphere. Along this longer path, much of the blue and violet light is scattered out of the direct beam. The remaining light that reaches your eyes from the direction of the sun is richer in longer wavelengths. Red, orange, gold. This is why the sun in nearby sky can appear warm at sunrise or sunset. The atmosphere has filtered the light by scattering. Small particles, dust, smoke, water droplets, and aerosols can deepen or change sunset colors. Sometimes the sky becomes pale peach, sometimes orange, sometimes deep red, sometimes purple after the sun has dipped below the horizon. A sunset is not simply the sun changing color. It is sunlight taking a longer path through air. The atmosphere becomes a vast optical instrument. It scatters, filters, and redirects light. The same physics that makes the sky blue at midday makes the horizon glow red in the evening. Only the geometry changes. Light's path becomes longer. Scattering has more distance to act. Blue is removed from the direct line. Red remains. There is something peaceful about this. The color of sunset is the atmosphere revealing the path length of light. You are seeing distance through air. You're seeing sunlight softened by its long journey through the lower atmosphere. A day ends in color because light has traveled through more of the world before reaching you. Chapter 9. Light as a wave. Now let us gently enter one of the deeper ideas. Light behaves like a wave. A wave is a disturbance that travels. A water wave travels across the surface of a pond. A sound wave travels through air. A wave on a string travels along the string when you shake one end. Light, however, is not a wave in water or air. Light is an electromagnetic wave. It consists of oscillating electric and magnetic fields. These fields change together and travel through space. This is a strange idea, so let us move slowly. An electric field is something that can exert forces on electric charges. A magnetic field is related to moving charges and magnetic effects. In light, the electric and magnetic fields oscillate or vary in a repeating way. The changing electric field is linked to a changing magnetic field. The changing magnetic field is linked to a changing electric field. Together, they sustain a wave that travels outward. Unlike sound, light does not need air. The electromagnetic field itself can propagate through empty space. This is why sunlight can cross the vacuum between the sun and earth. A light wave has a wavelength. The wavelength is the distance from one crest of the wave to the next. It also has a frequency. The frequency tells how many wave cycles pass a point each second. Wavelength and frequency are related. For light in a vacuum, shorter wavelength means higher frequency. Longer wavelength means lower frequency. Visible color is connected to wavelength and frequency. Red light has a longer wavelength and lower frequency than blue light. Blue and violet light have shorter wavelengths and higher frequencies. But visible light is only a small part of the electromagnetic spectrum. There are radio waves with very long wavelengths, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. All of these are electromagnetic radiation. They differ mainly in wavelength, frequency, and energy. The light we see is just a narrow band our eyes evolved to detect. The universe is shining in many kinds of light, most of it invisible to human eyes. Radio telescopes see long waves from space. Infrared telescopes see heat and dust. X-ray telescopes see high-energy events. Different wavelengths reveal different parts of reality. To understand light as a wave is to understand that the visible world is only one window in a much larger spectrum. Chapter 10, Interference and Diffraction. Waves can do things that particles in ordinary experience do not easily do. They can overlap. They can interfere. They can bend around edges. Interference happens when waves meet and combine. If two wave crests meet, they can reinforce each other. This is constructive interference. The resulting wave is stronger. If a crest meets a trough, they can cancel partly or completely. This is destructive interference. The resulting wave is weaker. You can see interference in water ripples. Drop two small stones into a pond. Ripples spread outward from each stone. Where the ripples overlap, patterns appear. Some places rise higher. Some places become calmer. Light can also interfere. When coherent light waves overlap, they can create bright and dark patterns. Bright where the waves reinforce. Dark where they cancel. This is one of the key pieces of evidence that light behaves like a wave. Diffraction is the bending and spreading of waves around edges or through openings. When light passes through a very narrow slit, it spreads out. When it passes through two slits, the spreading waves overlap and create an interference pattern. This is connected to the famous double-slit experiment. The double-slit experiment is one of the most important and mysterious experiments in physics. When light passes through two narrow slits, it can form a pattern of bright and dark bands on a screen. This pattern shows wave behavior. The light from the two slits interferes with itself. Bright bands appear where waves reinforce. Dark bands appear where waves cancel. But when we study light very carefully, we find another side of the story. Light also arrives in individual packets of energy, photons. This is where light becomes deeply strange. It behaves like a wave in how it travels and interferes. But it behaves like particles when it exchanges energy with matter. We will come to photons soon. For now, we can rest with the wave idea. Light can overlap with light. Light can create patterns from reinforcement and cancellation. Light can bend through small openings. Light is not merely a stream of tiny glowing beads moving in straight lines. It has wave-like structure, a rhythm in the electromagnetic field. Chapter 11, Light as Photons. Now, let us look at the other side of light. Light behaves as if it comes in packets. These packets are called photons. A photon is a quantum of electromagnetic radiation. That sounds technical, but we can think of it gently as the smallest discrete packet of light energy. When light interacts with matter, energy is often exchanged in these packets. This idea became necessary because of experiments that could not be explained by a purely classical wave picture. One famous example is the photoelectric effect. When light shines on certain metals, electrons can be ejected from the surface. Classical wave thinking suggested that brighter light should eventually provide enough energy to release electrons, regardless of color, if one waited long enough. But experiments showed something different. Light below a certain frequency could not eject electrons, no matter how intense it was. Light above that frequency could eject electrons, even if it was weak. This made sense if light energy came in photons, and the energy of each photon depended on frequency. Higher frequency photons carry more energy. Lower frequency photons carry less. If a photon has enough energy, it can free an electron. If it does not, increasing the number of low-energy photons does not solve the problem in the same way. Albert Einstein helped explain this effect using the photon idea. This was one of the key steps toward quantum physics. So light is not simply a wave. It is not simply particles either. It is quantum. It has properties of both, depending on how we observe and interact with it. This is called wave-particle duality. The phrase may sound mysterious, because it is mysterious. But we do not need to force it into everyday categories. Light is not obligated to behave like familiar objects. It belongs to a deeper level of physical reality. Sometimes a wave description is most useful. Sometimes a photon description is most useful. Both are part of our understanding. A photon has no rest mass. It always travels at the speed of light in a vacuum. It carries energy and momentum. It can be absorbed by atoms. It can be emitted when atoms change energy states. It can travel across the universe for billions of years before finally being absorbed by a detector, a telescope, a leaf, or an eye. Every time you see a star, photons from that star have entered your eyes. Light becomes vision through the arrival of photons. The distant becomes present. The past becomes visible. Chapter 12, the electromagnetic spectrum. Visible light is only a small part of a much larger family. This family is called the electromagnetic spectrum. It includes radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. All of them are electromagnetic waves. They all travel at the speed of light in a vacuum. They differ in wavelength, frequency, and energy. Radio waves have very long wavelengths. They can be meters, kilometers, or even longer. We use radio waves for communication. They carry signals for radio broadcasts, television, radar, and many wireless technologies. Microwaves have shorter wavelengths than radio waves. They are used in microwave ovens, radar, and communications. Infrared radiation is associated with heat. Warm objects emit infrared light. Your body emits infrared radiation. Thermal cameras can detect it. Some animals can sense infrared. Visible light is the narrow band we see. Red, orange, yellow, green, blue, violet. Ultraviolet light has shorter wavelengths and higher energy than visible violet light. Some ultraviolet light from the sun can damage skin and eyes. Earth's atmosphere, especially the ozone layer, absorbs much of the most harmful ultraviolet radiation. X-rays have even shorter wavelengths and higher energies. They can pass through soft tissue more easily than visible light, which makes them useful in medical imaging. Gamma rays have the shortest wavelengths and highest photon energies in the electromagnetic spectrum. They are produced in some nuclear processes, extreme astrophysical events, and high-energy particle interactions. The electromagnetic spectrum is one continuous range. The names are categories we use for convenience. Nature does not draw hard borders between radio, microwave, infrared, visible, and ultraviolet. The spectrum flows smoothly from long wavelength to short wavelength. Human vision evolved to detect a small window of the spectrum, partly because the sun emits strongly invisible light and Earth's atmosphere is transparent to much of it. So our eyes are tuned to a useful band. But the universe is full of invisible light. If we could see radio waves, the sky would look different. If we could see infrared, warm bodies would glow. If we could see X-rays, energetic cosmic events would stand out. Astronomy became much richer when we learned to study the universe in many wavelengths. Each part of the spectrum tells a different story. Visible light shows stars. Infrared reveals dust and warmth. Radio waves reveal cold gas and magnetic structures. X-rays reveal hot gas and energetic objects. Gamma rays reveal some of the most violent processes in the universe. Light is far larger than what our eyes can see. Chapter 13, How Eyes Receive Light. Seeing begins when light enters the eye. The eye is a living optical instrument. Light passes through the cornea, the clear outer surface. It enters through the pupil, the dark opening at the center. The iris adjusts the size of the pupil, letting in more or less light. Then the lens helps focus the light onto the retina at the back of the eye. The retina contains photoreceptor cells. There are rods and cones. Rods are very sensitive to low light. They help us see in dim conditions, but they do not give strong color information. Cones are responsible for color vision and sharper detail. There are different types of cones sensitive to different ranges of wavelengths. The brain compares signals from these cone types to create the experience of color. When a photon is absorbed by a molecule in a photoreceptor cell, it can trigger a chain of biochemical events. This eventually produces an electrical signal. That signal travels through nerve cells toward the brain. The brain processes patterns of signals: edges, motion, brightness, color, depth, shape. The visual world you experience is not simply copied into the brain like a photograph. It is constructed, interpreted, stabilized, compared with memory, connected to meaning. Light enters the eye as physical energy, but vision becomes experienced through biology and consciousness. This is one of the most remarkable transformations in nature. Photons from the sun reflect off a leaf. Some enter your eye. Molecules respond. Nerves signal. The brain creates the green of the leaf. Physics becomes perception. Energy becomes image. External light becomes inner world. This is why light is not only an object of physics. It is part of life, part of awareness, part of how the universe becomes visible to itself through living beings. Chapter 14, Light in Plants. Light is essential for plants. Through photosynthesis, plants use light energy to help convert carbon dioxide and water into sugars. These sugars store chemical energy. Oxygen is released as a byproduct. This process supports much of life on Earth. Plants do not use all colors of light equally. Chlorophyll absorbs strongly in the blue and red regions of visible light. It reflects more green light. That is one reason many leaves appear green. Again, color is a relationship. Sunlight arrives. Pigments absorb some wavelengths and reflect others. Our eyes receive the reflected light. The leaf appears green. Photosynthesis is a deep connection between sunlight and life. The energy in food often begins as light captured by plants. When you eat fruit, grain, vegetables, or plants directly, you are receiving stored solar energy. When animals eat plants, and other animals eat those animals, sunlight still sits at the base of much of the food chain. Even fossil fuels are ancient sunlight in a broad sense. They form from organisms that once captured solar energy, later buried and transformed over geological time. So light feeds a biosphere. It warms Earth. It drives the water cycle. It powers photosynthesis. It sets rhythms of day and night. Plants grow toward light. This response is called phototropism. A plant near a window may bend toward the sunlight. Cells on one side of the stem grow differently from cells on the other side, and the plant curves toward the light source. Life has learned to follow light. Leaves arrange themselves to capture it. Flowers open and close with daily cycles. Forests compete for it. Seeds sprout in response to it. Light is not only illumination, it is a source of order and growth. In the quiet body of a plant, photons become chemistry. Chemistry becomes structure. Structure becomes leaf, stem, root, fruit, forest. A beam of sunlight becomes life. Chapter 15, The Sun as a Source of Light. Most of the light in our daytime world comes from the sun. The sun is a star, a vast sphere of hot plasma held together by gravity. In its core, nuclear fusion transforms hydrogen into helium. This process releases energy. That energy slowly makes its way outward. The journey of energy from the core to the surface of the sun is not simple. Photons created deep inside the sun do not travel straight out immediately. They are absorbed and re-emitted many times. Their path is a kind of random walk through dense solar material. Eventually, energy reaches the outer layers and escapes as sunlight. Once light leaves the sun's visible surface, it travels through space. About 8 minutes later, some of it reaches Earth. This means daylight is slightly old. The sunlight you see now left the sun about 8 minutes ago. Not long compared with starlight from distant suns, but still not instant. Light gives us the universe with time delays. The farther away something is, the older the light we receive. The sun's light is also spread across wavelengths. Much of its energy arrives in visible and infrared light, with some ultraviolet. Earth's atmosphere filters and transforms that light. Some is reflected by clouds. Some is scattered by air. Some is absorbed by the ground and ocean. Some drives photosynthesis. Some warms the atmosphere. The sun is the main energy source for Earth's weather and climate. Sunlight warms different parts of the planet unevenly. The equator receives more direct sunlight than the poles. Land and ocean heat differently. Air moves in response to temperature differences. Winds form, clouds form, rain falls. The water cycle turns. So the physics of light is connected to the physics of weather, rain, climate, and life. Light from the sun is not simply brightness. It is the energy stream that drives much of the surface activity of our planet. Every sunrise is a star warming a world. Every sunset is that star's light taking a longer path through air. Every day is Earth turning through the sun's radiation. Chapter 16, Moonlight and Reflected Sunlight. The moon glows softly at night, but the moon does not make its own visible light. Moonlight is sunlight reflected from the lunar surface. Sunlight travels from the sun to the moon. The moon's dusty surface reflects some of it. That reflected light travels to Earth. It enters our eyes, and we see the moon. Moonlight feels very different from sunlight. It is dimmer, cooler in mood, softer, but physically it begins as sunlight. It has simply reflected from another world. The phases of the moon are also about light and geometry. Half of the moon is always lit by the sun, except during a lunar eclipse. But from Earth, we see different portions of that illuminated half as the moon orbits around us. New moon, crescent, first quarter, gibbous, full moon, then back again. The moon is not changing shape. The lighted portion visible from Earth is changing. The phases are quiet dance of sun, moon, and Earth. Light reveals geometry. A full moon occurs when the moon is opposite the sun in our sky, and the side facing Earth is fully illuminated. A crescent moon occurs when only a small part of the sunlit half is visible from Earth. During a lunar eclipse, Earth passes between the sun and the moon. Earth's shadow falls on the moon. The moon can turn a deep reddish color because some sunlight bends through Earth's atmosphere and reaches the lunar surface. Again, refraction and scattering shape what we see. Moonlight reminds us that not all light sources are original sources. Some are reflectors. The moon reflects the sun. Planets reflect the sun. Clouds reflect sunlight. A page reflects the light of a lamp. A mirror reflects your face. Much of seeing is seeing reflected light. The night sky contains both emitters and reflectors. Stars emit their own light. Planets and moons reflect. To look at the moon is to see sunlight softened by dust, distance, and night. Chapter 17, Starlight and Looking Back in Time. When you look at the stars, you are looking into the past. This is because light takes time to travel. The nearest stars, other than the sun, are several light years away. A light year is the distance light travels in 1 year. So if a star is 10 light years away, the light you see tonight left that star 10 years ago. If a galaxy is 1 million light years away, its light began traveling 1 million years ago. The farther we look into space, the farther we look back in time. Astronomy is a kind of time travel through light. We do not see distant objects as they are right now. We see them as they were when the light began its journey. This is not because our instruments are slow. It is built into the structure of a universe. Light has a finite speed. Information travels at a finite speed. The night sky is a layered history. Some stars are seen as they were years ago. Distant nebulae as they were thousands of years ago. Nearby galaxies as they were millions of years ago. Distant galaxies as they were billions of years ago. The most distant light we can observe from the early universe is called the cosmic microwave background. It is not visible light to our eyes, but microwave radiation. It comes from a time when the universe became transparent, about 380,000 years after the Big Bang. This ancient light has been traveling through space for over 13 billion years, stretched by the expansion of the universe. Light carries history. A photon can leave a star, cross interstellar space, enter a telescope and become data. Or it can enter an eye and become a tiny point in the sky. Every star you see is a message, a record of a distant furnace, a signal from another place and another time. This gives starlight a quiet emotional depth. The stars are not decorations on a dark ceiling. They are suns, and their light is old, patient, traveling for years, centuries, or longer. To look up at night is to receive ancient light gently. Chapter 18, Light and Time. Light is deeply connected to time. In everyday life, time seems to flow the same everywhere. But in physics, light helps reveal that time is more subtle. Einstein's special theory of relativity begins with a remarkable fact. The speed of light in a vacuum is the same for all observers, regardless of how they are moving. This is very different from ordinary speeds. If you walk forward on a moving train, someone on the ground measures your speed as a train's speed plus your walking speed. But light does not behave this way. All observers measure the same speed of light in a vacuum. To make this possible, space and time themselves adjust. Moving clocks tick differently. Lengths in the direction of motion change. Events that seem simultaneous to one observer may not be simultaneous to another. This can feel strange, but it is one of the deepest lessons of light. The speed of light is not just a speed. It is part of the structure of space-time. It sets the cosmic speed limit for information and causality. Nothing with mass can be accelerated to the speed of light. Signals cannot travel faster than light in vacuum. This means the universe has a built-in delay. The sun could not influence Earth instantly if something changed. The information would travel at the speed of light. Gravity waves also travel at the speed of light. Electromagnetic signals travel at the speed of light. The universe is not instantaneously connected. It communicates through time. Light defines horizons. There are regions of the universe whose light has not had time to reach us. There are events so far away that their signals may never reach us because of cosmic expansion. So light shapes what can be known. It draws the boundary between the visible and the unreachable. In this way, light is not only illumination, it is a measure of time, distance, and causality. A beam of light in a room is connected to the structure of space-time. A sunrise is connected to relativity. A star in the sky is connected to cosmic history. Light tells us not only what is there, it tells us when it was there. Chapter 19, Lasers and Organized Light. Most ordinary light is a mixture. A lamp emits many wavelengths and directions. Sunlight contains a broad spectrum. A candle flame flickers and glows with many colors and directions. A laser is different. Laser light is highly organized. The word laser comes from light amplification by stimulated emission of radiation. That phrase is long, but the basic idea can be approached gently. A laser produces light in which many photons share the same wavelength, direction, and phase. Phase means the timing of the wave cycle. When waves are in phase, their crests and troughs line up. Laser light is coherent. It can form a narrow beam. It can stay focused over long distances. It can create precise interference effects. Lasers are used in many technologies. Barcode scanners, fiber optic communication, medical tools, manufacturing, scientific experiments, laser pointers, optical measurements, data storage. The calm red dot from a laser pointer is not just a bright spot. It is organized light, photons acting together in a highly coordinated way. Lasers show us that light can be controlled with great precision. But even ordinary light has its own quiet order. Sunlight spreads outward from a star. Lamplight fills a room. Moonlight reflects from dust. Laser light travels in a narrow, disciplined beam. Different forms of light have different degrees of order, different sources, different spectra, different directions, different coherence. The physics of light is not one single behavior. It is a family of behaviors. A candle glow, a rainbow, a laser beam, a star, a phone screen, a telescope image. All are light, but arranged in different ways. Chapter 20, Screens, Pixels, and Artificial Light. Much of modern life is filled with artificial light. Screens, street lights, lamps, LEDs, headlights, Signs, displays. A screen creates images by controlling tiny light emitting or light filtering elements called pixels. Each pixel can produce or transmit certain amounts of red, green, and blue light. By combining different intensities of these three colors, a screen can create the appearance of many colors. This works because of how our eyes and brain process color. We do not need every possible wavelength to be physically present. If the red, green, and blue cone cells in our eyes are stimulated in the right proportions, the brain perceives a color. A yellow pixel on a screen may be made from red and green light together. A white pixel may be red, green, and blue together. This is additive color mixing. Light colors add together. It is different from mixing paint, where pigments absorb and subtract wavelengths. Screens are modern light machines. They turn electricity into patterns of photons. Those photons enter the eyes. The brain interprets them as words, faces, landscapes, films, and stars. This is remarkable. A glowing rectangle can create the impression of a sky, a wave, a forest, a galaxy, a diagram of light itself. Artificial light has extended human activity into the night. It has made cities luminous. It has made communication visual and instant, but it also affects sleep. Bright light, especially light rich in blue wavelengths, can influence circadian rhythms. Our bodies respond to light as a signal of day and night. This is why soft, dim, warm light can feel restful in the evening, and bright blue-white light can feel alerting. Light shapes not only what we see, it shapes biological time. It tells the body when to wake, when to focus, and when to rest. This is another way light is connected to life, not only through plants and photosynthesis, but through the rhythms of sleep, wakefulness, and daily experience. Chapter 21, Bioluminescence, Light Made by Life. Some living things produce light. This is called bioluminescence. Fireflies glow. Some deep-sea creatures shine in darkness. Certain fungi glow faintly. Some plankton create blue flashes in disturbed ocean water. Bioluminescence is light produced by chemical reactions inside living organisms. It is usually very efficient, producing little heat compared with many artificial light sources. In fireflies, light helps with communication and mating signals. In the deep ocean, light can help attract prey, confuse predators, communicate, or camouflage an animal against faint light from above. The deep sea is mostly dark. Sunlight fades quickly in water. Only a small fraction of light penetrates deep below the surface. Far below, many organisms create their own light. Tiny blue glows, flashes, patterns, living constellations in the ocean. Bioluminescence shows that light is not only cosmic or technological, it is biological. Life has found ways to make photons. A chemical reaction releases energy. That energy becomes visible light. In a firefly, the result is a soft greenish glow in summer air. In the ocean, it may be a blue shimmer around moving water. This kind of light often feels magical because it appears where we do not expect light to be. In darkness, in forests, in deep water, in living bodies. But it is physics and chemistry working through biology. Energy changes form. Molecules react. Photons are emitted. The living world glows. This is one of the gentlest sides of light. Not the blazing sun, not lightning, not a laser, but a small living spark, a quiet signal in the dark. Chapter 22, Light in the Atmosphere. The atmosphere does many things to light. It scatters it. It absorbs it. It refracts it. It filters it. It softens it. We have already seen scattering in the blue sky and red sunset. But there are many other atmospheric light effects. Mirages happen when layers of air at different temperatures bend light. On a hot road, air near the surface can be much warmer than the air above. This creates a gradient in the refractive index of the air. Light bends along the gradient. The result can look like water shimmering on the road, but there is no water there. The light has been bent by temperature differences in air. The atmosphere can also make stars twinkle. Starlight passes through turbulent layers of air before reaching your eyes. The moving air bends the light slightly in changing directions. This makes the star appear to flicker. Planets often twinkle less than stars because they appear as tiny disks rather than point-like sources. So the variations average out more. The atmosphere can create halos around the sun or moon when light passes through ice crystals high in the air. The crystals bend and reflect light in particular geometric ways. Sometimes you see a ring around the moon. Sometimes bright spots beside the sun called sundogs. Sometimes pillars of light rising from the horizon. Each effect is a message from light interacting with air, water, or ice. Even on a cloudy day, light is shaped by the atmosphere. Cloud droplets scatter sunlight, making the sky a broad, diffuse source. Shadows soften. Colors become muted. The world seems quieter. The atmosphere is not just something light passes through. It is an optical environment. A living layer of gases, droplets, particles, and ice crystals that continuously reshapes the light reaching us. The sky is a changing expression of physics. Chapter 23, Light and the Universe We Cannot Touch. Most of what we know about distant space comes from light. We cannot travel to the stars easily. We cannot collect pieces of distant galaxies, but we can receive their light. A telescope is a collector of light. The larger the telescope, the more light it can gather. More light allows us to see fainter objects. Long exposures allow light from dim sources to accumulate. Spectroscopy allows us to split light into its wavelengths and study the patterns. When we spread starlight into a spectrum, we can learn what elements are present. Atoms absorb and emit light at specific wavelengths. These patterns are like fingerprints. Hydrogen has its pattern. Helium has its pattern. Sodium, calcium, oxygen, iron, and other elements have theirs. By studying spectra, astronomers can determine the composition of stars and gas clouds. Light also tells us motion. If an object moves away from us, its light can be shifted toward longer wavelengths. This is called redshift. If it moves toward us, its light can shift towards shorter wavelengths. This is blue shift. The redshift of distant galaxies help reveal that the universe is expanding. Light tells us temperature. Hot objects glow differently from cooler ones. The color and spectrum of a star reveal its surface temperature. Blue stars are generally hotter. Red stars are cooler. Light tells us magnetic fields, rotation, density, and chemical composition. It tells us the structure of galaxies, the birthplaces of stars, the remnants of supernovae, the presence of black holes through the glowing material around them. Light is our messenger from the unreachable. It crosses space and carries information. When it arrives, we translate it into images, spectra, measurements, theories, stories. The universe speaks in light, and physics teaches us how to listen. Chapter 24, Light Near Black Holes. Near a black hole, light behaves in extreme ways. A black hole is a region where gravity is so strong that nothing can escape from inside the event horizon, not even light. Outside the event horizon, light can still travel, but its path may be strongly curved by gravity. Einstein's general relativity tells us that mass and energy curve space-time. Light follows paths through that curved space-time. Near a black hole, the curvature is intense. Light can bend dramatically. Some light can orbit briefly around the black hole before escaping or falling in. The region around a black hole may glow if gas and dust fall toward it. As matter spirals inward, it can heat up enormously. This hot material emits light, including X-rays and other high-energy radiation. The black hole itself is dark, but its surroundings can be bright. In images of black hole environments, we may see a bright ring-like structure. This light has been shaped by gravity. Some of it comes from material behind the black hole, but has been bent around toward us. Gravity turns space-time into a lens. This is called gravitational lensing. Black holes show us that even light, which travels so fast and seems so free, is still shaped by gravity. Light cannot escape from inside the event horizon. Outside, its path bends. Its frequency can shift. Its travel time can change. Light near a black hole becomes a way to study the strongest gravity in the universe. This connects our video back to gravity. Light and gravity are not separate stories. They meet in space-time. They meet around stars. They meet in the bending of starlight by the sun. They meet in gravitational lensing by galaxies. They meet at the edge of black holes. The quiet beam of sunlight in a room and the curved light near a black hole both belong to the same universe of physical law. One is gentle, one is extreme. Both are light, following the structure of reality. Chapter 25, a gentle summary. Let us gather the story softly. We began with a beam of morning light in a quiet room, tiny dust particles drifting through it, a soft patch of brightness on the floor. From there, we saw that light carries energy. It can travel through empty space. It can be absorbed, reflected, transmitted, scattered, and bent. We explored shadows where objects block light and create regions of darkness. We explore reflection where surfaces send light back. We explore refraction where light bends as it enters a new material. We saw that white light contains many colors. A prism reveals a hidden spectrum inside sunlight. We learn why the sky is blue. Air molecules scatter shorter wavelengths more strongly. Blue light spreads across the sky. We learn why sunsets glow red and orange. Sunlight travels through more atmosphere, and shorter wavelengths scatter away from the direct path. We entered the wave nature of light. Light is an electromagnetic wave with oscillating electric and magnetic fields. It has wavelength and frequency. It can interfere and diffract. Then we saw the photon side of light. Light is also exchanged in packets of energy. Photons. This led us toward quantum physics, where light is both wave-like and particle-like. We widened our view to the electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Visible light is only a small window in a much larger reality. We followed light into the eye. Photons became signals. Signals became vision. We followed light into plants. Photons became chemistry. Chemistry became life. We visited the sun, the source of daylight. We saw that moonlight is reflected sunlight. We looked at starlight and understood that looking into space is looking into the past. We touched the connection between light and time. The speed of light shapes relativity, causality, and the limits of what can be known. We looked at lasers, screens, bioluminescence, atmospheric effects, astronomy, and the bending of light near black holes. And through all of this, the same gentle idea remained. Light is a messenger. It carries energy. It carries information. It reveals matter. It reveals distance. It reveals time. It lets the universe become visible. Chapter 26, Closing Reflection. Light is so common that we sometimes forget to wonder at it. A lamp on a desk, a reflection in a window, the color of a wall, the glow of a phone screen, the blue of the sky, the gold of sunset, the pale light of the moon, the small white points of stars. But every one of these is part of the same larger story. Electromagnetic waves, photons, energy, matter, time, vision, the universe sending messages across space. A beam of light can cross a room in almost no time. Sunlight crosses space in about 8 minutes. Starlight may travel for years. Galaxy light may travel for millions or billions of years. And then, after all that travel, it may enter an eye, strike a sensor, warm a surface, feed a plant, or form an image. Light is motion made visible. It is energy in transit. It is the bridge between distant things and awareness. If you are resting now, you do not need to hold all of this in your mind. You can let it soften. Let the science become gentle. Let the beam of morning light become simple again. A soft line across a quiet room. A few dust particles drifting. A window. A floor. A calm beginning. The physics remains there, whether we think about it or not. In the color of the sky, in the shadow of a tree, in the reflection of the moon, in the warmth of sunlight, in the glow of a distant star. The universe is full of light, some visible, some invisible, some new, some ancient, some gentle enough to fill a bedroom, some powerful enough to reveal galaxies. For tonight, you can simply rest inside the thought that light is still traveling, across rooms, across skies, across oceans of space, from star to planet, from lamp to page, from moon to window, from the world into your quiet eyes. Let the light fade softly now. Let the room become dim. Let the ideas settle. And let yourself rest. Sleep well. If you enjoyed this calm journey through the physics of light, you can return anytime for more gentle physics stories about waves, time, fire, stars, black holes, and the quiet laws of the universe. For now, thank you for listening, and good night.